All right, so we've got an example where we've got a small town with two grocery stores, Archer's Market and Eva's Shop. While some of the customers are completely loyal to one store or another, there's another group of customers who change their shopping habits each month. Of the shoppers who favor Archer's Market one month, only 70% still shop there the following month, while Eva's Shop retains 78% of its customer base each month. Everyone in town shops at one of the two stores. There's no other town, and there's no out of town that shop at either store. So they're completely isolated. We're only looking at these two. If Archer's Market currently has 2,500 customers and Eva's Shop only has 1,900, we want to know how many customers Archer's Market is going to have next month. So what we'll do is we'll use this information to create a transition matrix. So if we know we've got Archer's going to Archer's and Eva's information, we can kind of set up this transition matrix. So if Archer's is retaining 70% of its market, then 70% will continue to be there next. However, 30% will go to Eva if 70% stays. Now, as far as Eva goes, 78% is retained. So Eva will have 78% go to Eva. What that means is that only 22% will go to Archer. So this is something we need to be careful about when we're creating these transition matrices, is that the way things are phrased doesn't necessarily mean that the probabilities all go in a particular row. It means that they go where the combination of rows going to columns happens. So be wary of that on the homework. Now, what we're told is that there are currently 2,500 people going to Archer's and 1,900 people going to Eva's. So, because these are raw numbers and not probabilities, we'll still multiply the same way. It'll just change slightly the context of what's going on. So we've got a 2 by 2 matrix, 0.7, 0.22, 0.3, 0.78 as our entries. And we have a 2 by 1 matrix with 2,500 and 1,900 as its entries. So if we take A times B, we'll get 2168 and 2232. So if we're looking for how many are at Archer's Market, that's going to be this first entry. So Archer's Market will have 2168 customers next month. So in this scenario, when we're multiplying these together, it'll tell us the number of customers we expect to shop at the store each month. It won't tell us how many have switched stores, because this is referring to all customers, not just the people that are switching. It does have a meaning, so it's not going to not have any meaning. And we don't have percentages here, we have raw numbers. So because we have the raw numbers, it's telling us how many customers are going to be at each shop next month. So if we continue to multiply this matrix together and raise it to a higher power, it's going to represent in the second row first column entry, because we have, again, we have Archer and Eva, and Archer and Eva. It'll tell us the probability of going from Archer's Market to each shop instead. So we're leaving Archer, going to Eva between months 3 and 4. So this isn't so much the switching from Archer's to Eva's that month. It tells us the probability of customer who's currently at Archer's Market being switching to Eva's shop in 3 months. So it's not so much if they're between months 3 and 4. If they're at month 3, and we're talking about using month 3 to predict month 4, we would just use this matrix one time. But if we're trying to go ahead and talk about what happens many months from now, that's when we need to raise this to an exponent, and that's how we get to this. So we're going from archers to Evas, and that's somebody who's currently there now, not somebody who will be there in the future. Now suppose that we found a steady state equilibrium vector for these 1126 and 1526 being the steady state for this. We want to know what the steady state vector means in the context of this scenario. Well, what it tells us is the long run probability of shopping at Archer's Market versus Eva's. It doesn't tell us the probability of switching, it tells us the probability of shopping at one versus the other. And it also doesn't tell us necessarily about the market share, because that would imply that we've got direct control over that, and there isn't some sort of ebb and flow that's happening, right? We still have people that are leaving Archer's Market and going to Eva's shop, and we also still have people going from Eva's shop and going to Archer's Market. So it's not so much a control over that percentage of the market share, it's more the probability that you'll end up shopping in one place or the other. And then last but not least, we want to verify that this is a steady state for this Markov process. So what we'll do is we'll take our matrix of 0.7, 0.22, 0.3, 0.78, and we'll multiply it by this 1126 and 1526. So we'll do that. So we've got already our matrix A. We just need to write in what we are assuming the steady state vector is. So it's one thing if we have to go ahead and find the steady state on our own. That's a different process. But if we're just verifying, we can go ahead and just multiply our matrix by our steady state and verify that that's still what we get. So B fraction version is what we have. So if we take A times B, and again we want the fraction version of that, we do indeed get back 1126 and 1526. So indeed this does check out, and it does end up being a steady state vector.